And clap. There we go. There we go. Again, I apologize. Late as usual, because again, there's going to be an additional constant in nature. I'm going to be late, or something like that. Or if I'm early, I am late in some other form of the multiverse, as I grasping for straws there for that analogy. But hey guys, what's going on? Memes here. Yes, yes. A little locale. And yes, I'm wearing a Pooh Bear good at doing absolutely nothing shirt. Why? Because that is what I am wearing right now. And number two, it does actually help elucidate, if you would. See, I can use some fancy words too. It helps to bring attention to, let's say, basically an object in motion tends to stay in motion. One that is already in motion tends to stay in motion. I know, we're going back to good old Newton here. But the question is, what can we learn from Newton? He's just a dude that invented calculus. Well, technically, I think Leibniz probably invented it first, but being the most powerful scientist at the time, he was good at claiming for many things. But he did many things, so he earned his clout. Also, rumor has it historically he may have been a dick. Now, one can be a dick and still notice things. I may be an example of that. Then again, it is my middle name. I'm literally the son of a dick. But I digress. The whole thing we're doing right now is we have our standard models of cosmology and stuff. And I'm just going to lay it out as we're starting the broadcast, and we're going to ease into it right now and everything as different folks are joining us from around this internet of stuff and things, and those who will be joining us temporally in the future, algorithm willing. But all right, so we have our standard. Oh, while we're doing this, I should probably erase this from yesterday's little talk. But we have our standard Lamba CDM. What the heck is that? Lambda, we tend to envision that as the cosmological constant. Perhaps it is the dark energy that, to the concordant model interpretation, yeah, that's what we call the standard model of cosmology. It is the concordant one. Why? Because that's what we call it. But it's basically you have this dark energy that seems to be expanding space-time itself, but we're maintaining an energy density through it, so we're totally not breaking any laws of thermodynamics or anything. Why? Because it works. It's again, that's one of the reasons why it's like it raises some questions and stuff, but if it is the best, simplest model that we have at this time to explain the observed phenomena, then okay, why else would people use it? It's probably the same reason why people use string theory and everything. And
Venus and the moon?
Oh, where is it? Oh, that's Venus? I was wondering what that was. Thad was just pointing out that Venus is very clear tonight. So if there's some place that's dark, feel free to check it out. Positioning and observational ability may vary depending on where you are. Something about spheres, it doesn't matter.
Right next to the moon, so it's easy to find.
Oh, yeah, I just looked up. I'm like, I saw it the other night. I think it was like over there. And I'm just looking up at it. And I'm like, all right, so that's very bright. I don't think it's twinkling, because if it was twinkling, that would mean it's most likely a star, because then the atmosphere seems to interfere with that wavelength. Oh, is that why they need to go to like the Atacama Desert and space to observe like the CMB?
Yeah, they try to get
because once
minimum atmospheres,
right,
minimum water.
Yeah, because I think once you're getting to the lower wavelengths, there it becomes an issue, because you can get down to about, I think, like 3 or 4 centimeters before the atmospheric gases really start getting in the way. That's why you want to go somewhere dry. But all right, little Moon and Venus tangent aside. All right, so our standard model. Big Bang cosmology. Again, I am not a professionally trained physicist in the standard arts or something like that. I'm a dude on the internet that's paying a lot of attention to a lot of smart folks that may actually be joining us right now or at some point there. So let me grab.
Do we have a fixed topic for today?
We're exploring alternative cosmological models.
Oh,
that is the
talk about not seeing Herman. That's Let's respond to what he said. Did you finish his video?
I'm almost done there. I'm going to be a little
Okay.
cautious. With that gentleman, I like the bit of his jive. I think he was playing fast and loose with some of the things with the podcast host that he was. We were just talking about. Hold on, I'll bring it up. It was just so folks actually know what that and I are talking about. We are talking about. Where is that gentleman? It was so many tabs. Oh, here we go. All right, I'm not going to close. All right, so let's share with the class. We'll do share the astounding mysteries of the self and universe. Physicist Nassim Haramein. And let's listen in real quick.
Basically, it's the smoothie universe. You just got to think of it that way. And now you can start to see, yeah, earlier on when I was presenting in physics, they were telling me planets are
Okay, so basically it's a nearly a 3-hour podcast and everything. It's hey, if that's your type of thing, you can go into it. I do agree with a lot of things because I believe this is partially I'm semi-subscribed to the gentleman hosting, Aubrey Marcus, there. So I'm interested in the occasional discussion that's relevant to me, not enough to watch every single uploader. We'll have that clog my feed there. But basically, they were inferring, talking about, well, the yin yang is like a torus and everything.
Yeah.
And I brought that up to Thad before and everything. And then the more and more I think about it, I'm like, all right, well, you could deform each area into the circle. And then if you have a center point going through, you could just kind of combine them. I'm like, oh my God, would that be the easiest way to get ChatGPT to try to code like a figure eight, not be like, take a yin yang, deform it into this, and then just connect it. And then just be like, all right, now turn that little toroid loop, that wormhole, if you would, and then just put a figure eight in it. That may be the easiest way to actually bring that up. But I digress. We'll say hello to the folks that are there. I know Hex has been waiting. Welcome, Hex. As ways, Gay Show, Upcycle. Oh, and Digital Pollution. Oh my God, Jez, I almost forgot your name. So this is the problem with the internet. You meet people, they use certain handles, and then all of a sudden they lose that handle. They swap between this, that, or the other thing. Or God forbid, they change their profile picture. And it's like, I'm looking at the same thing. I'm reading the exact same words, but the image next to it just throw my mind for a wobble. It's kind of like when Bone shows up and when he's in his cat form. And then I'm like, all right, it's Bone, who's usually appears as a dog, but then is in a cat form. But all right, so since we've talked about the random stuff and things of, we're boggling in my mind for a moment, let's start off with, before we get into the alternative models, yes, I know, bait and switch, everybody. These things happen. But before we get into the alternative models, let's start with what we know, or the best to our knowledge here. All right, so what we're going to do is we'll just bring up over here. Let's just do the standard concordance model. I apologize. I said Concord or something. I think that's a video game that didn't do well recently. But what do I know? I haven't been in that realm for too long recently. All right, so let's go to our little pictures here. We'll share with the class. This is okay. This is brought to us by NASA. So, all right, Lamba CDM, aka Lambda Cold Dark Model. All right, so we got this thing here. All right, so where do we start? I'm going to do a very poor attempt at illustrating that picture in a slightly different way. All right, so according to the deep lore of current cosmology, we start off with cosmic fluctuations. Yes, if you watch some physicists, they will actually be waving their hand. I'm like, all right, magic. Or some sufficient quantum fluctuations. That's not magic. What is that? That's something we're trying to quantify that's unquantifiable. All right, to me, that kind of sounds like magic. Or an unknown at this point. All right, so we start off. We have a point of an infinitesimal point where everything of existence is squeezed into. All right, we got our point here. Okay. Yes, that's not infinitely small, but I can barely see it, and I'm standing right next to it. All right, we apply our hand-waving cosmic fluctuations, and then kaboom. We get something from nothing, whatever that means. And then we kind of go, okay, so we go out like this, and it's, many people believe, and even Roger Penrose gives it a little bit here, we get a period of expansion, where what happened? Universe as we know it increased by 78 orders of magnitude, and like I can't actually snap my fingers. That was a skill I never learned. That or whistling. I'm very, yes, basically. Now is it a full Planck time that they say inflation, or is it like half a second or something?
No, 1 Planck time.
That's okay.
For the first epoch.
All right, so for inflation,
Yeah.
that's the current. Okay, so according to the Thad, we have 1 TP. All right, and this would be T equals 0, T equals, we'll do big I, inflation, inflate. Okay, so 1, we've got 1 tick of the clock, 78 orders of magnitude, and then we're in a really hot, dense state, and then according to models, once we get, I think it's around like 380,000 years, so we got 380,000 years. Oh, we're gonna get all messed up because we're going from years to light years and everything there. Well, actually, no, we can just do time there. It's a weird one. We're doing light year. What does that mean? Well, it's a period of time. It's also the distance that something travels. We can use it as a metric. Why? Because we're dealing with ginormous numbers here. All right, so at around 380,000 years, we got cool enough. I believe it's about, I think it's around 3,000 Kelvin. Last time I had heard 3,000 Kelvin. We release the CMB, the cosmic microwave background. That's what Professor Keating and the good folks at the Simons Observatory, they've gotten first light, at least at the beginning of the year.
What was the temperature at the first tick?
Oh, the temperature at the first tick. What we believe. Okay, so all right. So the temperature at about the first tick, we're gonna go with. It's probably about big T, CP, which is about equal to 10 to the 32 degrees Kelvin. It might be about. After that first tick, it might actually be about 10 to the 30-ish Kelvin, because I think there's like an 8 pi difference depending on when you do your Schwarzschild metric and everything. For at least a Planck mass black hole, it's 8 pi under the actual Planck temperature. But okay, for observers like us, we would be fried either way. Okay, so it's a good thing we're not there right now. All right, so we continue on, and then we get to our current epoch. We get about 13 point, I'm gonna say 7, because I like writing 137 billion years. Billion years. For notation wise, that's billion is 10 to the 9, so that's, was it I can do
13.7
1 point, there we go, 37 times 10 to the 9 years.
No, 10 to the 10.
Oh, 10 to the 10? Okay,
Yeah.
I was, 13. All right, 10 to the 10. Okay, I won't dwell on that. You do so much numerology, you look at that, I'm like, wait a second, that's about the inverse of the energy density per cubic meter or so. It's off by like about 4. Not that that's the discussion for right now. We're merely taking mental notes, because as you go through things, and sometimes you think things, sometimes you'll do calculations, and then sometimes you're actually trying to explain and share with the class and see what other people are thinking, and you actually hear the words coming out of your mouth for the first time, and it's like, oh, I now see why Professor Wolfram does that, because it helps make you better and at least engages different neurons that you may not have used in a particular way. All right, so we're at about 13.7 billion years right now. All right, what is that? This is approximately now, give or take a little. That's our best estimates, and then all right, so it's about 13.7 billion years old. Okay, so we've existed, so we've come from this point, and we're progressing outward, following our world lines and everything out there. And we start to get our particles and everything. We'll put a little bit of particles there. We'll have some electrons, and then we're forming molecules, and other things are coming together. And eventually, we're getting bigger things. We'll get like some stars, get some planets around those stars and everything. And our cosmological model is going to progress, and then we'll get galaxies, because we represent galaxies with little spinny things coming out of them, because that's our general thought of them and everything. And then you're going to get clusters and superclusters and black holes and supermassive black holes and maybe some ultramassive black holes. All right, so this is where we're at. What now? So the current model, as far as the general understanding, is, well, it seems like our universe is expanding. So what's it going to do? It's going to continue to expand. And the wonky thing is, apparently, our cosmological constant, I believe that's related to the Einstein kappa, which is like 10 to the negative 42 or 43, something like that. I've got a calculation somewhere on the channel of it. But the problem is, it seems like the expansion that we have is accelerating. WTF? It's like, all right, hold on, wait. If we start off, when we have a big bang, we're going to be expanding. It's like, well, surely we're going to run out of some juice, and it's going to slow down. That's what everyone was expecting in the late 90s. But I still remember being in school, and they're like, no, it seems to be going faster. And I'm like, what? How is that even possible? Okay. How might it be possible? Well, that's a great question. Well, maybe everything's just moving further and further away, since maybe we only have a finite amount of matter. So as things are spreading out, we're just going to lose all control. It's like stretching out a piece of gum. Imperfect analogy, but eventually it's going to get thinner, and then might just have a big rip. What does that mean? That would be a very bad day for our reality. Because if reality ends up tearing itself apart, the fabric of space-time, where we live, ain't going to exist. So at some point, we're just going to like go poof, non-existence, enter another dimension. I don't know. Maybe we'll be at King Yama's check-in, kind of like in the Dragon Ball universe. I don't know. Haven't been there. All right. So we've got a potential for a big rip. It reminds me of something I saw on Twitter, but it's not for the sake of this discussion. I'll show some folks later. So we get a big rip. Okay, so that'll be number one. We could have a big rip. Eventually, at some point, obviously far in the future, because we don't want to panic people. And again, at least according to our calculations, we seem to be at some point. This has to do, I think, like with the top quark and stuff too, where I know, oh, he's talking about particle physics now. This is supposed to be about cosmology. It's funny how these things seem to keep going with each other. But according to, I believe, the standard model, we're in a metastable state. You look at some of the graphs, and it's like, all right, if it was any further, we would be in an unstable state. If we're an energy level slightly below that, we would be in a stable state. We literally exist in the Goldilocks zone of metastable. Yes, more hand waving is literally in here. I'm adding that for semi-dramatic effect. Okay, so that is another wormhole. We'll have to talk about that another time. And by that, I mean I actually need to learn what it actually means before I would even attempt to speak anything more than just repeating the words that I read. Okay, so I got a big rip. What's the other possibility? Well, it is also big. Number 2, we could have a big crunch. Yes, crunching into it like a Pringles, like a Kit Kat bar or whatever you want. So crunch. Okay. So this again would be bad for us. Because what happens? All right, let's say that accelerating, whatever it was, maybe it was a fluke. Maybe we're totally wrong or something. Or what if we start to measure it and then we seem to be actually slowing down? What happens if this spreading out of space-time itself, our universe expanding into nothingness, because we have no concept beyond that within the concordance model mostly. If we're going through and all of a sudden we start losing juice, gravity takes over, we're just going to go literally back to start. That could be bad for us because that could also be a big bounce. Maybe we just crush down. Maybe we just will no longer exist, possibly. I don't know. Haven't been there. But, okay, maybe we were all there at some point if there's something to that. But what happens if we just go down and we bounce back out? Maybe we get down to a point around here, not quite there, slightly smaller, according to the current. If you take the mass of the observable universe, you have to crush it down to its Schwarzschild radius. I believe Planck density, that brings us down to about the mass, the radius of a proton. I think it's about 10 to the minus 15 in there. So yeah, we've been crunched down really small. Unfortunately, all our tables and chairs and this stuff as we know it, at least to us, it probably isn't going to really have much of a meaning anymore. We're going to be in like a super hyper dense state at that point. And then we can have another big bang, cosmic kablooey, whatever you want to call it. And then we just reiterate. Is that a version of the many worlds? I don't know. If you invoke infinity, that could be a possibility. That could be happening again and again and again. What is this? Is this like the 137th iteration or something? I mean, that would be kind of cool. Also very terrifying at the same time. But, okay, so we get to those points. And, okay, no, I'll call it back. But we can go through these different iterations. All right, this is what we generally assume is what might be going on. We do have some other models. We have Sir Roger Penrose's conformal. I'll put it over here. We have something like this. Conformal, cyclic cosmology. Okay, so the conformal cyclic cosmology. What is that? All right, well, basically, Professor Penrose, he starts off something like this. He's not the biggest fan of inflation, so he has a really small area down there. But he has these things. Each iteration he calls an aeon. All right, so basically, if you look at how he generally has it there, he has it something like this. We'll have basically what we had there, and then it iterates into another one of these, and then it iterates into another one, and another one. Yes, and then we just go on and on, my friends. All right, so we can also draw this kind of more like a cylinder, or just ease of what the heck might be going on. So he's like, all right, you get to a point where things would basically, all stars would just end up burning out. You just have a whole bunch of ginormal, massive black holes and maybe some photons around. And since photons don't experience time, it's going to be pretty boring there for most folks. And then it's like, all right, you're going to get to a point where there's going to be some geometric thing that goes on, and somehow via conformal transformation. I think he's using, I forget whether it's either affine or non-affine spaces. Was it?
I thought they were using fiber bundles.
I mean, it's at some point. I mean, Professor Penrose works on all different stuff, so sometimes my mind just kind of blends them together. But basically, you have different aeons. That's what he calls them. I don't know how to spell A-E.
A-E-O-N.
A-E-O-N. There we go. A-E-O-N.
Some people pronounce it.
I know. I always just learned, like, you would call it an eon. What is an eon? An enormous, just expenditure of time.
That's what it is. It's just English pronounce it a little different.
Right. So yeah. Like, well, they still have you in color, so it's okay. Nobody's perfect. But you would continue on. At some point, you're going to have your conformal transformation, whatever happens there, and then you would have like a new Big Bang. So you would do that again, and we do it again, and on, my friends. So that's the view. I mean, I'm kind of sympathetic to that because, well, number one, again, total bias here. I mean, I totally stole the name for what I refer to as eternal cyclic cosmology. Yes, the bait and switch to promote your own work. Why? Well, it's a topic. And number two, I wanted to go back and just at least hear myself start to say the words of the standard accepted models, a couple other models. And I'm realizing now as I'm speaking these words, wow, I do not know anywhere near enough. But let's see what else we got. Upcycle is commenting that, well, the conditions in the early universe were similar to those in a nuclear reactor. When things become uncontrollable, it leads to runaway behavior, consequential expansion. Well, that is very true. But then again, it's, see, part of, I think, the issue we were into is when we use the term universe. It's a very encompassing term because we're talking about everything. So if we're going to be talking about everything, that is the system that it is part of. Whereas if we're dealing with a reactor, that's basically a subsystem of the system. So the reactor is going to be within the nuclear facility itself, hopefully designed well with proper safety protocols and everything in there. It's going to be generating energy, and that's why we need the control rods, because we need to absorb some of the neutrons, because we don't want it to be a runaway chain reaction stuff. I'm also a personal proponent of believing that we require more thorium, because I think the technology in that is actually reaching the point where we could actually do that and it would be worthwhile, at least a stopgap, till we get to fusion. But okay, so we've covered a couple of standard general models in a very minute way. So my big thing is, okay, I see these pictures, and we'll share the picture. Let me just change my audio because I went back to the other one. Let me audio. Oh, never mind. Nope, it's picking the stuff up too. Okay.
I can talk.
Continue. Yeah.
Okay, so far you laid out some standard ways of talking about how the universe evolves over time.
Mm-hmm.
All right, but we can also throw in details that all of these models would agree that despite the evolution differences, they would all say the features of the universe that's evolving are that it has electrons, protons, neutrons, right? That it has the interactions between those three things define the constants of nature, and so on. Like, so the measurable features that are actually present during the evolution are also things we could put into the story. And it's surprising that it's such a small number. I mean, it's a big number, 288 features, constants, right? But still, it's surprising that it's not, way closer to infinity.
Mm-hmm. Anytime you're dealing with less than infinity, that's a good thing, because now you're at least finite.
Yeah. Anyway, I just wanted to add that. These different philosophical discussions about how the universe evolves are great, because to answer them, you're going to have to key into different features or things that you're going to be able to measure and so on, right? But that means that you have to be more specific about what features actually exist in these universes that we're talking about. And it's a small list. It's a relatively small list, something that a single individual human can play with. Like, you play 500 piece puzzles. 288 pieces is just half, roughly.
Yeah.
Anyway.
Well, then again, we're also hoping that we have all the puzzle pieces and stuff, because if you're missing a piece, it's kind of hard to complete the puzzle. Perhaps the puzzle piece that we're looking for is actually made up of a couple other things, or maybe one of the pieces is stuck together.
Yeah, and what is this puzzle? It's a thing that try to metaphysically think about. What's this puzzle we're trying to solve, and what does it do for us when we solve it? Like, literally what it does is it allows us to on purpose do any transform that can be done, not ones that can't be done. You can't now do magic and have a power that doesn't exist in nature in any way, right? But you can do ones that don't tend to exist in large form, like, a lightning bolt. You can make a lightning bolt on purpose. That would be really anyway, the model itself, basically putting the puzzle together, allows you to then look inside and see every single gear, every single way that you can twist the model. So every single, we've been saying Markovian transform that there is in the system. So every state to state you can transform in, and that means absorbing energy in different directions and different amounts and so on. But still, it's just state transforms.
Well, it's I believe quantum theory has been using Markovian, but the big thing now is kind of like the non-Markovian, where basically the past matters and everything. So rather than just taking a single snapshot and having, if we know everything that's happening right this second, we'll be able to predict what would happen from there, and then go on and on and on, the standard Laplace's demon, something along those lines, imperfect analogy. But non-Markovian, what preceded, the history makes a difference, and I'm still trying to grok that.
It means there's a more than one step in time in the transaction that's holding something together. It's not just a single step in time that they can keep it. Does that make sense? So if you have a system that's larger than the Planck time reach, which is the Planck length, right? If it's bigger than that, it's going to take more than one Planck time cycles to traverse it. Yeah. So if you have a structure that's made out of a lot of things, something that's many atoms large, that's many Planck things, then you can have transforms in it that aren't just single step transforms at the bottom. There's complex spreading things out transforms. That's
anything we do is going to ripple throughout whatever the system it is.
Yeah.
So wherever we are, wherever we're trying to measure, we're just measuring the dynamics of that system, employing the scientific method to limit the unforeseen things and try to account for as many of the infinite things as we can in order to get the best accuracy possible. So my thing is, I'm very biased, but I look at these things and I'm like, all right, so we keep showing, hold on, I'll show the other model real quick, just, it's a much better, pretty thing to see. Oh, quantum age conics. Hey, good to see you, Hex. All right, our other Hex there. All right, so let's go to, there we go. Boom, our friend here. Okay. As we see, we start, we have our quantum fluctuations. Everybody wave their hands. Okay. So we start, we spread out, we get to the present day. Okay. So we can stop that screen right now. All right. So we have our little thing spreading out here, and just as somebody that's played with a lot of different toys and coloring books and stuff like that, I'm like, wait a second. What if we just did something crazy? All right. What if we just connected it? Oh, that gets into the next model. We get, oh God. What does Professor Tura call it? A minimal Lamba CDM model. So, okay. So we get, well, erase stuff here. Already gone through. All right. So Number 4, minimal lambda CDM. All right. So what the heck do those words even mean? Well, you're gonna have to check the paper for yourself to actually verify the words coming out of my mouth. The long story thought of like what is actually going on is Professor Turok, he's claiming that in their formulation with Turok et al., they were rewinding GR. And as they're rewinding GR, they come to, again, we generally think of this as a singular point here, but they use a particular transformation where the claim was they end up just passing straight through that singularity or whatever that point might be, and they come out on the other end, and what they see is literally a mirror universe, whereas the terminology used. So what might that mean? It's like, oh, we're just seeing a reflection of what we saw over here. I'm very sympathetic to that model because, again, a lot of inherent bias because what do we just do? We just kind of connected this. How did we connect that? Well, what if rather than just a mirror, if it's a mirror, what is it mirroring? Why might it look the same? Well, what if we went this way? We just continued ourselves around till we got here. We go around here, and you get to here, and you go through a very small point where maybe everything's going to get dense. Maybe as it's getting dense, maybe it's getting hot, and maybe it looks like a big bang on the other side. And at that point, you might say that this system is or at least to observers like us, our universe or realm of persistence. Is there something outside? I don't know. There'll be dragons. That's why I like the realm of persistence, because it's basically where we live. It's what we can observe. Like, oh, you can't say that. Oh, you're not explaining anything out there. Listen, I'm just saying that Professor Gödel apparently was able to show that you can't actually prove all of mathematics, because at some point you're going to have an axiom of faith that you cannot prove within the system of the rules. You literally need to be a higher level up, and basically you would need an oracle or something, or programmer of the rules or something to tell you that that is actually correct. I'm sure I butchered that statement, but the general thought process there is, if you cannot actually prove within the system the rules of the system, ultimately you must have an article of faith. And you sit back and you're like, wait a second, this sounds very familiar. And even Professor Wolfram brings this up a fair bit. He's like, some of the discussions that we're having nowadays were discussions that we had millennia ago about all these different things. And it's like, it seems like some of the answers from the theologians in back of the day may actually hold up to some scrutiny right now. And that's kind of an amazing thing. And when I say scrutiny, it's like, all right, somebody can propose something scientific. Maybe it gets something. It could be completely wrong. But if you're giving a very generalized response saying the universe occurs in cycles, again, according to maybe many standard or concordance generalizations, it's like, oh, that's preposterous there. And then you go a little bit away to, well, what happens if it's crunching down and going? Isn't that a cycle right there? What happened? Oh, we're going back. We have some mathematical calculations and everything. And then if you use 36 like zero-dimensional fields, you can get Professor Penrose's model all and everything set up there. It's okay. Maybe that's the case, but I'm like, okay, well, what if it literally just cycled through? How could that be the case? Then you would have perpetual energy. Now, perpetual energy, as we know, according to the maths of matter and everything, you can not create a perpetual motion machine of the third kind. What is the third kind? One that does not have any outside influence. But if it's perpetual motion, it's not actually supposed to have outside influence in everything too. Now, if we're going to go through and try to do that, now matter has, we'll do the quick calculation there, because basically the number of iterations that matter can go through, since matter is let's go over here. No, and I'll go to our friend here, and we have lambda. There we go. So basically the calculation is, if you take Planck's constant, not the h bar, but the full Planck's constant, you divide it by 4. That's a little shortcut there. Wait, what did I do? Planck's constant divide. Okay, I did that totally wrong. Hold on, let me go to Bekenstein bound. Bekenstein bound. So many. Oh, quantum speed limit is the keyword. Quantum speed limit. All right. So we go to the Bremmerman's. Okay. I put the 4 on the bottom. There we go. 4 divided by Planck's constant. All right. So over there we have. All right. So the maximum amount of action you could have would be 6.037 times 10 to the 33 seconds divided by kilograms of meters squared. Inverse angular momentum. What the heck does that mean? Okay, we go to our friend over here. What does this actually mean? Okay, so what this actually means, over here. All right. The quantum speed limit. Bounds. Establish an upper bound at which computation can be performed. Computational machinery is constructed out of physical matter that must follow quantum mechanics, and each operation, if it is to be unambiguous, must be a transition of the system from one state to an orthogonal state. Suppose that the computing machinery is a physical system evolving under a Hamiltonian that does not change with time. Then, according to the Margolis-Levitin theorem, the number of operations per unit time, per unit energy is basically, all right, that's processing rate of all forms of computation cannot be higher than this bound per second per joule of energy. All right. We're going to get into some fun stuff. Oh, hey, Rick, I think you're going to like this part. All right. So what do we do? Well, let's give it the maximum amount of energy that we could. Planck energy. All right. Energy. Planck energy, go.
Yeah.
All right.
So assume we have a replicator that's maximally transforming.
So, all right. So we got 4 over the Planck constant times the Planck energy. It gives us this. It gives us 1.1808 times 10 to the 43 hertz. Thanks to our good friends at Wolfram Alpha, we can see that that comes out to be about 0.64 the Planck frequency. But let's do it a little further. Let's take our whole expression here and let's divide it by the Planck frequency. Let's see what we get. Is there some type of insight that we could get for the maximal amount of action that could take place per unit of energy per second of time? Or energy per second. Maybe I shouldn't have used the unit there. But okay, we get 0.6366. That doesn't mean anything to me. So we take a little copy of it. We plug it in. Let's see, is there any type of simple geometric form that we could see in this relation? Oh, look, 2 divided by pi. Wait a second. If we see that, that must mean that if we go back and we take the Planck frequency, we copy that. Let's divide this whole thing into the Planck frequency. Oh, that gives us this number right here, 1.5708. All right, let's see what that means. We go in, we take a look. Oh, imagine my shock. Pi divided by 2. I know. Oh. I have no... Okay, I have no idea if our audio just completely dropped out or not. Hold on, let me see. Let's double check on ourselves here. YouTube. I just noticed it looked like it swapped to something. Let's see. Channel. Are we still? Okay. All right. We're still here. I have no idea. Okay. It seemed to get. Okay. All right. There we go. All right. The inversion is dead. No, I just went to YouTube and I just brought it up. I wanted to see. Okay, still there. No, I had the settings thing there and it said it was on some other thing. So I had no idea if it swapped over. It said it was working in here. But when your configurations are different in different areas, it makes one wonder what might be going on there. So, okay. So let's go back. And go back to our friend. Okay, so what the heck were we even doing? Go to our answer over here. Okay, so what the heck did we just do? We get a pi over 2 term. What's that? All right, the curvature relationship with a circle, divide by 2. What were we actually solving for? Oh, we were dividing the Planck frequency by the maximum ability of, how do they say it? It's the processing rates of all form of computation. Okay, so the maximum rate of computation for matter itself per second per joule of energy is pi divided by 2 relationship of the Planck frequency. I thought that was kind of cool. And one of the reasons I got there is because I had originally done it squared. And one of the reasons I paid attention was because if we do this guy right here, so we just square this whole guy, all of a sudden, we get 1.394 times 10 to the 86 reciprocal seconds, aka vorticity advection. Vortices, they say. That's times to the -2, aka Hertz squared. I remember Rick had come and given a talk, and he'd kind of boiled gravity down to that, and that was a very interesting thing. And that's one of the reasons I paid attention to this, because then you're just going to get the same thing, essentially, just in whatever form it is. So you just do that. I think it's the same relationship. Let's see. So Planck frequency. Planck frequency divided by. Wait, what do we do? Oh, wait, no. Duh. Those are both the same. Nope. Divide 1 into the. God. Oh, it confuses the heck out of it when you have seconds. Once you get past something squared or some weird units, -2. There we go. Boom. Now we divide. Boom. And. All right. Yeah, so you're basically getting, I believe that's the same thing out. So, I'm supposed to square that term. Derp. There we go. All right, so it's some other iteration of pi. So this one is, I think, pi divided by 4 or something, maybe 2 pi. Let's see. Boom. Pi squared divide by 4. There we go. All right. So, all right. Oh, cool. Oh, I liked Archimedes' law of gravity. That was a fun one there. But okay, so we had that. All right, let's loop ourselves back around. All right, so we're looping ourselves back around. So again, we're going to conjecture here. We have this concordance model. All right. I'm like, is it that much to ask to maybe what if we literally loop back around? Let's say we are about 8 orders of magnitude larger. So if standard measurements of our realm or the observable universe, so the obs uni. Bob's uni it's about 10 to the 26 meters. Okay, so I would claim that conjecture uni, as we know it, is about 10 to the 34 meters. All right, so what does that mean? All right, we're about 8 magnitudes larger. So add about 8 zeros onto our standard concordance as far as we've observed within the observable universe. It just means it's a lot more ginormous. So if it's a lot more ginormous, if you're trying to do your standard, well, we need to measure curvature. What do? Well, we draw a little triangle on the sky. Maybe we draw a big triangle on the sky. Now, the thing is, you're going to need to measure a big enough triangle in order to detect curvature. Currently, if universe, we believe, is like this big, and we're drawing triangles like this, and we're like, well, it looks flat. Okay, maybe it is flat. Maybe it's just so gimongulous that our current measurements, maybe we need to go up another several orders of magnitude before we actually start to detect curvature. Might just be a bunch of bunk. Might also provide an explanation. So, all right, let's make this a little prettier because it's gotten very unpretty right now. So I've just written and drawn a whole bunch of lines. Let's get to the whole bait and switch. If we're going to bait and switch, let's switch to something good. Let's see if we can't account for the majority of our observations and the effects cosmologically in the simplest way possible that we could probably, maybe at least most folks could probably start to intuit. Because for me, it's like, all right, how do I imagine this? All right, so we're going to imagine a system. For argument's sake, we will call it universe. I prefer realm of persistence, but we'll digress. So our realm in which we live, I would say imagine the most beautiful snow globe and then do some fusion with a lava lamp. Okay, that's my general way to explain it. So how are we going to go about this? Let's see. Is this guy good? Oh, all right, that's pretty good. Okay, I can't get something from nothing, so we need to invoke either the Roolead, a void of just random waves and something. We need to take form, and that form we're going to invoke is the figure 8 knots. So we're just going to do a little figure 8 here. Perhaps, and again, it's actually going to be in a toroidal state. I'm going to claim. All right, it's actually the complement of the figure 8 knot. The actual action gives rise to that torus boundary. All right, once you have that, if you have your realm with infinite, got a little model over here, something kind of like this. It works better with a structure rather than having to cut it all out. All right, so we got these little cutouts here so you can kind of see the little figure 8ness in there. Okay. So imagine you got this, you take this form. Why? It's made as a double cover of the Giesecke manifold, which is the minimal volume 3 manifold right there. All right. So once we get that, that takes form. Take all those waves and whatever is out there, and then just have it start to come in. And you're just going to have this massive amount of energy, and then we're going to have some form of an inversion. And the inversion of a torus is a hypersphere, which I learned from, God rest his soul, John Williamson was able to go out and find, and yes, there is some literature on it. I needed to delve into it further, but I'm like, all right, get that hypersphere. I'm like, okay, if this thing starts to spin, and you've got some of this spinning going in right here, and that's rotating around, well, if it has the ability to ingest something, something comes in, all right, So whatever ends up happening, it's like you have the inversion, you're going to have a hot, dense state. It's probably going to look maybe kind of like a Big Bang or something if we're going to start from there. And again, that's a lot more speculative. But the highest speculation, I would say, is, all right, what do we have? Matter, antimatter as we're going out. I'm like, well, what's the simplest thing? What particle, as we might refer to, as its own antiparticle? The photon. So if we let there be light, and if this thing was able to condense things into maybe neutrons or something, shout out to Kali for neutron decay cosmology. Now she's calling it quantum cyclic cosmology or whatnot. You're going to have it excreting whatever matter. And if there's a preferred direction, I don't know, does that explain chirality? Especially maybe if you have some rotational component there. All right, we'll end with a speculation. Let's just view it as it is. Okay. So what if something like this is, well, we kind of have our standard. Oh, wait, this picture's looking awfully like what we had before. Wait a second. You have all your stuff going out, and that forms into its things. It's stars, it's galaxies, it's clusters, it's superclusters, all our fun other stuff over here. Bada boom, bada bing. Okay. Now, if this is absolutely ginormous, like this is 10 to the 34 meters. There it is. All right. This is going to be pretty ginormous. It's going to look pretty dang flat, no? So, there. All right. So if you got this stuff and it's going out, and we add, marker that. Trash. All right. So if we add a little rotation, we got some rotation here. It's like, well, wait a second. Now, maybe this thing's spinning at Planck frequency or doing something crazy like that. Maybe that is the case, but that would create some form of, let's say, maybe a space-time gradient, if you would, just kind of like in a washing machine. If you have something spinning in the center, it might not be doing much, but eventually, given enough time, if you start gaining angular momentum and stuff kind of starts going around, it's like, well, that might provide an explanation for inertia. I mean, I'm sure there are probably better explanations, but for at least this model, that is part of what we may get out. But the main gist is this stuff is coming out, and we've got a hypersphere. At some point, this stuff is going to spin around, and if it's coming out this way, at some point, the stuff is going to loop around, and maybe if you were to run certain equations, you would end up getting back out what would appear to be almost, I don't know, a mirror universe, perhaps, as worked out by Turok et al. So it's a very lopsided one. Well, then again, maybe that would be more accurate. A little asymmetry within our symmetry. But the whole point is, as you have what we may observe as a hot, dense state, a Big Bang, if you would, perhaps we're just kind of a bit of an island floating through the cosmos. And, well, because at one point, you're going to have all these galaxies, these ginormous superclusters and everything, and these hypermassive black holes and everything, they're going to feed back in to what we would say is our field configuration. Because ultimately the claim would be, if we're going to have a field configuration utilizing the hyperbolic figure 8 knot, using it to model the 5 bases of reality, the Planck constants, time, space, charge, mass, and temperature, if it has these particular actions and it's taking a form such as this, well, as things loop around, they can go back into that little throat of that vortex there. Some folks may say it's a wormhole, if you would. If if it's getting all sucked down to a super about 10 to the 18, which is right about the charge radius of a neutron there, to that level, what might be coming out is going to be extremely hot, dense, and may resemble what we may observe as a Big Bang, cosmic kablooey, call it whatever you would. But the ultimate claim is that once you have a balance such as this, it will persist. And at least according to Professor Sean Carroll, when one is dealing with infinity, eternity is a long time. So does that mean that if we were to, again, make the giant leap that, all right, if it persists, does that mean it's Turing complete? At that point, does that mean we could engage in all these different articulations so that the only difference after an enormous amount of time, maybe 10 to the 38 Gregorian years, but who's counting? You may attain the exact same configuration as we are right now, except instead of me drawing a right arrow, I draw a left arrow first. Okay. Now, that seems crazy. Oh, how could everything get into the exact same state in the configuration? Now, again, if we're talking about infinity, or the lemniscate, which technically that is, that's a long time. And again, if you have an infinite amount of time, and if you had a finite amount of space, you could go through every single iteration where everything may end up happening. Is that many worlds? Would you have every single potential configuration at some point? Maybe. Now, not all configurations may take place within the limit of whatever happens. Just because something could happen doesn't mean it necessarily would. But I don't know. It sounds kind of a little bit like an easy out in that, I don't know, maybe we're going to get many worlds for free, or at least maybe it'll make some folks happy. Is the ultimate answer? Again, I don't know. I'm not an outside observer of our realm of persistence. I'm part of the system in which we live. I think it's a pretty cool system because we can actually think about these things, and we may actually have the potential to figure out what's going on. But yes, there's let's see what else we got. All right, existent. See, here's the thing up cycle, commenting about helical magnetic fields existing in the early universe. Now, I can't confirm or deny that. Again, I wasn't there, but we seem to like to ignore that because until more recently, we really haven't had many measurements or the ability to really measure significance of what might be going on electromagnetically. So a lot of times we just discount that and we're like, it's about this far away. We figure out it's about this much mass. Let's apply like 4 or 5 significant digits of gravity and let's go. All right. You can use GR and everything to try to figure out at the different rates and at the super massive levels, try to account for more variables and everything. But very often, we ignore a lot of the electromagnetic effects. I am also biased, but I'm like, well, if even a neutron ends up emitting some form of a charge, but it's neutrally balanced. Yeah, so yes, on average, but it still kind of has those 2 charges there, and it's made up of things that have charges and everything, to our knowledge. But ultimately, we are even going for over an hour. So, the tokamak. Oh yeah, the little thing right there. It's very interesting. All right, we'll end on this. So you all heard of the tokamak, those little like toroidal donut things. So we get the tokamak. Let's go to the naughty. I spelled that wrong. Naughty, not a Tron. There we go. Because this is actually a thing. Yes, it's not just a troll like memes on the internet. This is from Princeton Plasma Physics Laboratory.gov, introducing the Nautatron. A Nautatron is a magnetic confinement device with a magnetic axis that is ambulant isotropic to a knot. Yes. So they're attempting, looks like the trefoil right now. Did they upgrade it? Let's see. No, this is 2014. Yeah, they're still using the trefoil knot. I would beg to make the claim that I think if we're going to get fusion off the ground, I feel like the HF8 reactor will probably be the way to go. That's just a personal opinion right there. Again, I'm very biased on that, but yeah, just a little bit of food for thought. So that's all we got for right now. Hey, peace out, everybody. Take care of yourselves. It's a crazy world out there, but I think 2025 is going to be quite the surprise. Peace out.